Good afternoon, Africa. Good afternoon, BIM Harambee Africa, and good afternoon to all of the participants of this conference, wherever you are. First and foremost, we want to take this time to thanks and appreciate the BIM Harambee Africa for organizing this important event. We are in the digitized world, and currently building information modeling is the industrial revolution that is sweeping across the construction industry, and Africa cannot be left behind. So BIM Harambee Africa, thank you for this worthy initiative. We really, really appreciate you for organizing this for Africa. Having said that, my name is Muniru Nyei. I'm a research student at the European Master's Program in BIM Advanced Building Information Modeling. My topic is Interoperability in Structural Engineering, a study of direct link data exchange between Revit, BIM platform, and FEM tools. I'm with the European Master Course. It's an advanced course. It's the first of its kind to be organized by the European, which through the Erasmus Mundus program, where it is being funded. I have a master's degree in structural engineering from the University of Bologna in Italy. While I was in Bologna, I traveled to Germany for an exchange program where I did infrastructural planning at the semester level. And then I had my bachelor degree in China back in 2015. Institutions and collaborating partners for this research work. This is currently a master thesis that is being conducted at the European Master Course in Building Information Modeling, BIM A+, which has been sponsored by the Erasmus Mundus project. The Erasmus Mundus project is an educational initiative by the European Union that supports intercultural collaborations, youth mobility across Europe, and sometimes other students from other parts of the world benefit from that. There are 3 collaborating universities of this master course, this program. You have the University of Minho, is located in Portugal, in Guimarães, and the University of Ljubljana in Slovenia, and you have Politecnica di Milano in Italy. And these are the collaborating partners where students attend courses in one country and do the thesis in another country. Currently, I'm based in Ljubljana, even though I live in Germany, but I have to move here for this program. And I'm collaborating for my master thesis, I'm working with Sophistic. Sophistic is a finite element or structural design companies that provide software solutions for structural design. And Sophistic currently is at the heart. It's one of the main software that is used in building information modeling, along with Revit in structural design. And we will say more about this later. Politecnica Engineering and Architectura is a company that I'm collaborating with. They are providing me the data to do the structural design aspect of this thesis. So having said that, what is BIM? We will touch about BIM. I know this is all about BIM. A lot of speakers have spoken lengthily about BIM, so I'm not going to bore you down with many explanations about BIM. I'm going to go directly into the subject matter, maybe just few definitions. And we'll talk about interoperability. This is a very important concept when you talk about BIM, when you talk about collaboration. People should be able to share information. And when they share the information, they should be able to use the shared information. And I will talk about BIM in structural engineering, which is the context, which is the heart, the theme of this topic, how to apply BIM in structural engineering. This will be demonstrated by case studies to see how interoperability works, how BIM is applied in structural engineering, as you will see later. The objectives of this study. Presently, I try to present an overview of BIM and how it provides useful platform to enhance the workflow of structural engineers. We'll examine the application of BIM in structural engineering, from modeling to analysis, design, and documentations, how all of these is performed on one platform. We elaborate on the three main levels of interoperability or data exchange in BIM structural engineering, which has to do with direct native file exchange. And the next one is direct link exchange and IFC. When you talk about BIM in structural engineering, these are the three levels of interoperability that are currently identified to work. But there are other ones, which this topic does not cover as well, but there are other ones, but the key ones are these ones. Through the case studies, we will assess the effectiveness and challenges of interoperability. The goal, the goal of the project is to acquire in-depth knowledge in the application of BIM in structural engineering, its technical capabilities and challenges associated with data exchange between mainstream BIM platforms like Revit and widely used FEM tools in the AEC industry. AEC represents architectural, engineering, and construction industry. Methodology. The methodology is based on data exchange. So what are we going to do? We are going to see how do you build a Revit model from a structural engineering point of view, or you get a model from an architect as a structural engineer, and you pass this model to the FEM solution or structural design softwares like Sophistic. We use RFM and CI Engineer to demonstrate this. What are we going to use? Which method of interoperability? We use the direct link. That is, these software are directly connected to Autodesk Revit. So within Revit, on one platform, you are able to perform multiple analysis using one platform. This is really beautiful. It's the beauty of BIM. Previously, these were not possible. So this is the methodology used in this project and how to move from one place to another, as you will see when we go along. And what is BIM? A lot of people have already spoken about this. I'm not going to waste a lot of time on it. Just that there is a specific definition of BIM that is very catchy, that is attractive and innovative, and it encompasses, it include all of the definition of BIM just in one paragraph or in a sentence. Is this definition proposed, presented by Jerry Lasserine. Jerry Lasserine is a building information enthusiast who says that BIM creates and maintains in real time multi-dimensional data-rich views through a project lifecycle to support communication. BIM helps to support communication. What does that mean? It helps to share information. So I share my information with the architect or the MEP engineers or the facility manager and collaborate. We are able to collaborate on the shared data. You make your comment on it and ask me to change something, and I ask you to change and simulate. With BIM, you using shared data for prediction. You can use you can create a BIM model, and this part is really also very good for structural engineers, where you can see the simulated models, and then you are able to determine how the structure is behaving, and you can just see everything, and it's very good. Optimization, where you do your design, you use feedback on shared data to improve the design. Maybe you want to optimize on economics, on economic design. You want to optimize on the design solutions, which kind of design you have. Everything is possible. There are a lot of things possible for this. And documentation and delivery. You can document it and then you deliver it. Everything is summarized with this graphic where you do the conceptual design, detailed design, construction, operation, rebuild, where you want to rebuild the facility or you want to do the restoration, recycling, and revitalization. Everything is right within there. This is the beauty of BIM. It presents everything where one model, you can use it for multiple uses and reuse, and use. This is very cool. While we're talking about BIM and interoperability, I would like to define briefly what is structural engineering, because this is at the heart of this discussion. When our audience are able to understand what is structural engineering, then they will follow this presentation in a most coordinated way. Structural engineering is a branch of civil engineering that deals with the analysis, design, and construction of load-bearing horizontal and vertical structure. As you can see, I underline, I highlighted load bearing. The structure must have the capacity to bear load. Then definitely you are talking about structural engineering there. So the structural engineers, somebody who is trained as a structural engineer should have the skills in determining loads and stresses for this load-bearing structure acting on the body. He should also be able to investigate the strength and behavior of the structural element, such as something like beams, the columns, the foundation. And he should also ensure that the economic feasibility and safe design, all of these are embedded within structural engineering. It's a specific branch within civil engineering that has to do with that. When you go downtown Johannesburg, most of the high-rise buildings, you go to Kenya, the long buildings, you talk about the Kenya Railway Network, those bridges. When you go downtown Manhattan, all of these high-rise buildings, these magnificent FTC, think about a structural engineer. That's the guy who takes the work of an architect and then he puts it into reality. Without this guy, the architect will just make something aesthetic. I'm sorry for the architects there, but then he's the one who put life into the architect's work. Yeah. Then we talk about structural engineer's role in BIM workflow, what he does, what he's supposed to do. He will be the one who create the structural model capable of, that is capable enough to facilitate analysis and design. His model should contain key structural parameters of materials like material properties, the boundary conditions, the loads, the section properties, the load combination, etc. We'll talk more about this later on. He should ensure that his structural model is intelligent, cost-effective, construction sequence of the structural elements are well under control. Now, having said that, this is what mainly his role is in the design process. For, as we say, he can get the drawings from the architects. He takes the drawing and then based on the structure he wants to design, if it is a concrete structure, a steel structure, he analyzes the materials. He assigns material parameters and properties to it based on the code. And then with his knowledge and experience and also the situation where the structure is located, and then he's able to assign loads and analyze these loads through what? Analyze all of this through a mathematical models and formulation, and he is able to define or determine the internal forces. These are internal forces such as the moments, the shear force, the normal force, the torsion or torque. Once you do these things, these are done through analysis in the software. Sometimes it can be done, some can be done through hand calculation as just as a backup. Then you will need to do verification. Some verifications of the structural elements will be done. These verifications are like you are designing your structure. Structural design is like resistance versus action. If you push me, I should be able to put up enough resistance. My resistance must be more than your action. And once my resistance is more than your action, it means that my structure is well fit. So he compares the resistance against the action, and the resistance must always be greater than the action. This can be verified through the codes, through his experience, through training, teaching, and everything. Now, before we go further, the last thing we would like to define and clearly understand, provide a little understanding about is FEM, finite element modeling. The word finite, small particle, finite element modeling. This is at the heart of structural calculations and analysis. All of the computers you see, they are based on finite element modeling. And finite element FEM is one of the three methods structural engineers generally use to determine internal forces and moments of structural system. Generally, there are three main methods. There's a force method out there to determine internal forces or displacement of the system. You have the displacement method, the FEM. You have the reduction method, which is also based on FEM. This method, the displacement method, is the backbone of most of the computer software. This guy that you see out there, they are based on the displacement method. So a good number of structural engineering software tools are based on principles of FEM or finite element modeling. So it is very important. That's why it's very important. A user of the software, it is very fundamental to understand the underlying principles behind the governing equations, the mathematics, and the mechanics on how the structural software compute internal forces using the FEM. Because without a deeper understanding of the basic principles behind the method, you are unable to do critical assessment of your computer results. It's not possible, thus the render that will render your analysis irrelevant and unsafe. So the FEM is a is basically a numerical approximation technique which require the division of structural system into a number of finite elements, as I just mentioned. The word finite. These elements are then connected to each other by the nodes. For each element, you do equilibrium conditions, as you will see here, and followed by a linear system of equations to solve the unknowns. All of these are are done behind the computer. As you are pressing the keyboard, this is what happened behind. So as you can see the demonstration here, normally you do it like you divide a structural system into element. For each element, you compute the element stiffness matrix, like the computer does it. For each element, you transform the load acting on within the element into equivalent nodal loads. As you see, you will see later, you create mesh. The software will create a mesh, you define the mesh. And after defining the mesh, the system compose the element stiffness relation for that particular element. And then it assemble all of them and calculate them. And then you consider support conditions, such as fixed support, which kind of support condition you have to consider. The software will determine the displacement vector. Sometimes some of these things could be calculated, but the equations can be so large. So that's why the software takes care of it. And then the software gives you the internal forces. Based on these internal forces, you are able to design your structures. So basically, this is just a little overview of finite element. To learn about this, it requires a huge, this takes a whole semester to learn this in universities. So normally, people in structural engineering, people in mechanical engineers, even sometimes electrical engineers, most of their calculations are based on finite element method. It's a very wide field. Then we would like to talk about interoperability. Oh, this is very important. What is interoperability in the midst of all of these we are discussing here? Interoperability, as the word entails, what is it? What kind of system? What kind of interoperability? How is it achieved? Let's look at the word itself, the definition. Not the definition, but just the word interoperability. Interoperability. The word inter means between two groups. Operability means things are able to operate in just a literal sense. The way that's another way to look at it, or the ability to keep a piece of equipment or system or the whole industrial installation into a safe and reliable functions conditions according to predefined requirements. So when you combine both, you must get to this definition that is presented by the ISO standard, which says the ability of two or more system or components to exchange information and to use the information that has been exchanged. It's not just exchanging the information. I must be able to use the information that I exchange. Otherwise, it's irrelevant. When an architect gave me his model, I should be able to use that model to alter the models and do my structural calculations. If I cannot, then interoperability does not exist. It should contribute to integration and elimination of information waste. So as you can see here, system A works together with system B, and then they are able to exchange information and they use those information. Interoperability it's a generic term. Every domain, every discipline has a way to define what really interoperability is. It depends on how you look at it. For BIM structural engineering, we're going to look at the various level of interoperability later on, but it has multi-dimensions, like 3 dimensions, the kinds of methods. It has a kind of system and he has a kind of interoperability. The kind of system we'll be talking about maybe non-technical interoperability and technical interoperability. Technical interoperability will be information system. That's the classical one. And the non-technical one would be like business, interoperability between business, organization, project, people, how they operate. And maybe the next one, the kind of interoperability could be this part has to do with semantic, the data connection. This is what we will be talking about more, how to exchange one data, the structural data, the syntactic, the connection data, and all of this. And the kinds of methods has to do with which method you use to achieve interoperability.
Like you have openness, you have machine reliability, industrial standards like the IFC, like you have the PDF document you use. All of these are all methods that give you interoperability. And then you have the ISO step physical files and all of these. And having said that, we now go to types and levels of interoperability in BIM structural engineering. Interoperability directly beneficial or related to structural engineering aspect, the direct native file exchange, the direct link data exchange, the IFC or OpenBIM. We will explain this later. And as you can see here, um, the direct native file exchange, what is it about? These three interoperabilities that I'm just about to explain are the one engineers use, especially structural engineers, to share information with each other or collaborate. So like the direct native file, for example, this is the level of interoperability that is based on proprietary format, and it exists between the software from the same company. For example, when you share Microsoft Excel documents, spreadsheet, and Microsoft Word documents together, and then you use the information, that's direct native file exchange. They are from the same background, the same companies. And when you do an AutoCAD, you take an AutoCAD first floor plan, for example. I can take of just, if you have a 10 floor story buildings, as a structural engineer, I would just tell you, give me your AutoCAD floor plan. With your AutoCAD floor plan, I can connect it to Revit, and then I can build the columns and all of the structural part on it. When you do that, that's native, direct native file exchange. File exchange between the Allplan Nemetschek software products, for example, the sharing of Revit models with Navisworks for clash detection, scheduling, and cost estimation, because Revit and Navisworks are all from Autodesk, the same company. So when you share information between the two of them, these are interoperabilities from the native file exchange method. And this is the most basic level of exchange, which allows the users to exchange data in their application software. But one of the main disadvantages of this interoperability is that it requires a repetitive process, which makes changes to the models very difficult. And at this level of interoperability, when you have a huge project, it's really, really a problem, you know? Yeah. So we go to the next one. The next one is the direct data exchange, which is the bidirectional or round tripping engineer. This is very good. This is the one, the structural model data is directly shared or exchanged between a BIM authoring tools. Let's underline this word, BIM authoring tool and an FEM software tools. What is that? BIM authoring tools are something like Autodesk, Tekla, maybe Tekla and ArchiCAD. If you are able to take your model from one of these and send it to an FEM or structural engineering software and perform analysis, what are you doing there is you are doing direct link data exchange or round tripping. You're going to see a lot of this in the case study. This is the backbone of this research. This research is trying to analyze, to understand the advantages and disadvantages of this method to a structural engineer, the fidelity, how important when you exchange the data, how this data can maintain their fidelity, they are not able to be compromised. We're going to see this later. Their studies have shown that this level of data exchange is the most effective and efficient method for BIM structural engineer up to date. It provides an interface for two independent software programs to exchange construction data in real time. This is really good. You're going to see this. Some examples are when you exchange your data Revit to Sophistic, Revit to Tekla, Revit to Dluba, which is RFEM, Revit to SAP, Revit to Autodesk Robot, Revit to CI Engineer, Revit to CI Engineer, Revit to Allplan, for example, or ArchiCAD to any of these. When you do that, you are talking about direct native file exchange. For example, you can see, as you can see here, you have the Revit model, and then right within the Revit platform, you exchange the data to CI Engineer and you perform your analysis, you are able to bring your data back and query it and make some changes and bring it back again. This is what we call round tripping. We will see more of this. And then the next one we talk about, which is highly been discussed by most people, is the inter the IFC, which is the Industrial Foundation Class. This is an open standard system that promotes vendor neutral and usable capable across the wide range of hardware devices, software platforms. This one is like basically like I'm sharing my file with someone else who also has a BIM tools that is able to read this file. In this one is neutral. You don't need to buy, just exchange your data. This is developed by the International Alliance for Interoperability. The open nature of the IFC allows the file to be read by any CAD software which have the IFC export and import functionalities. And this is really good. This is good for coordination, especially for structural engineering part. The disadvantage of this with the structural engineer is that IFC is mainly used for coordination purposes, but not for structural analysis because of its low capabilities in transferring structural properties and data. Yes, I can use my IFC model, my structural model, and convert it to IFC and send it to the architect in my office or in the other companies or the contractor. He can only take the model and for coordination purpose. But when he gives me his model, for example, the architect, I'm not able to use that model to perform structural analysis in reality because the IFC does not really there's a problem with currently there's still a problem because this research was able to unveil that there's still a problem with the low combinations. The some material properties still cannot be transferred correctly. It's still a problem. But I guess the IFC, the building smart, is working on these things to make some of these corrections so that IFC can not only be for coordination purposes, you can use it for structural analysis and design purposes. Yeah. However, don't take my word for it. There are also some companies that are using it for design purposes, but then they have to add extra innovation and technologies to make some code changes, some API and all of these kind of stuff. Yeah, these are the current versions of IFC. This should be the candidate that should be up anytime soon. IFC 4.3, you have IFC 4.2. Some of these are retired as well, but these are the IFC version. We're not going to go into all of these detail, but this is an example of IFC file exchange. I did it some time ago. This is a frame system, and I did it in Revit, and then I converted it to an IFC file, and I went to ArchiCAD to see what happens, and then I receive it I export it on ArchiCAD, and I open the ArchiCAD. This is what happens. This is what I saw. As you can see, so if I was exchanging this with an architect, he was going to be able to see it, and I could tell the architect, oh, there's problem with the column, the thickness, there's a problem, and then the architect could make the changes and send it back to me when I see that change, and then I can be able to modify it and do my structural calculations without the IFC anyway. So this is just an example. So this is what happened. There has been a significant improvement in data exchange in the AEC industry. Could you imagine this chaos? These bidirectional exchanges between architects, structural engineers, you change it, come this way, bring it back. This is really chaotic. This is some years ago. But now with the beam, the open beam, the IFC, everything now has been synchronized and integrated. You are just able to have one database and you exchange all of this information. Very good stuff. BIM in structural engineering. Um, there are BIM uses. What is BIM use? BIM use refer to the BIM uses refers to the way in which the concept of building information modeling is applied or used in each specialist domain within the project life cycle. The way an architect uses BIM is a little different from the way a facility manager will use it and a structural engineer will use it. The way you use it, maybe the architect use the BIM for analysis of energy analysis. Maybe he use it for facility management. The guy in facility management use it to keep track of the facility. The structural engineers BIM uses as identified has got many BIM uses, but we are able to identify three key BIM uses for a structural engineer. One is interdisciplinary coordination, project documentation, producing construction drawing, structural analysis and design through third-party analysis, plugin or direct link, as we just mentioned. Interdisciplinary coordination, there's a team composed of architect, composed of mechanical engineer, composed of facility managers. How do you share these informations? How do you have a one data and then you use it? You are able to coordinate. This is really good. This is good, important for a structural engineer. Project, how are you able to document your project is very important. For structural analysis and design, we're going to see this. This is going to be our focus. You're going to see how this works. And structural BIM model. There are structural BIM models. There are two types of the structural BIM models. You have the physical models versus the analytical model. The structural BIM model is the central data that you establish in Revit or in Akika. In Revit, you build your models and then you populate your data, your models with data. For example, your column and everything, your beam, your slab, you have the all of your metadata, all of the information about that column. Anybody who comes and click on it, they can see all of those information. These are all the central data, which is the structural BIM models. But then what will be the physical model? When you The physical model represents the exact geometry of the structural members. It is a model void of the architecture and MEP elements of a BIM model. That is, when you take away the MEP, the electrical components, the mechanical components, and from the architect side, you don't need the windows, you don't need the door as a structural engineer. All you need is the structural elements. There's a physical component. That's why you're going to do your analysis with. That's the model left when we extract the load bearing structural components of the structure. So this is the physical model. As you can see here, there's no window. In order to perform a structural analysis on this, you don't need the windows, you don't need the doors, you don't need some partitions, you don't need the mechanical equipment. This is what you use. So that's what we call physical model. In Revit, when you are creating the physical model, if you use you have to be cautious. You should use the template. When you use the structural templates in Revit, as you are creating the physical model is creating automatically the analytical models. And it is this analytical model you're going to use to perform your analysis, the structural analysis. And this is what you're going to transfer to the FEM software or the structural engineering software. So that's why we say it is the transition between the software, the BIM software, and the FEM software. Without this, interoperability is impossible. It is the basis for structural calculations, analysis, and design during the exchange. Then the next thing we want to talk about is structural engineering BIM workflow. The workflow, how do you perform your workflow? How do you start, what do you start with, continue with, and end with? Normally, there are a lot of workflow out there. Your company or your institution can establish their own workflow, but basically from structural engineering point of view, this is how it is. So it's just a modification of it. And this is exactly what you're going to see in BIM. Mostly, you will create your BIM model of the structural elements. From that BIM models, the physical model will be created in Revit. And then from that, automatically, you have an analytical model available for you where all your load are added and materials. And you transfer it to an FEM models, the FEM software, which is the finite element software. In this model, you are able to perform analysis and design. Analysis and design are two different things. Analysis is when you compute, you calculate the internal forces of the structural element. These are analysis. And then you see what the internal forces are, what the stresses are. Design is when you use that internal forces to design that particular element. For example, you want to design the slab or the column. You are using the code, and then the software are also able to compute that, but then you have to follow a specific code guidelines how to do the design of that structure. When you are done with that, you do what? Reinforcement generation and detailing, as you can see here. With the reinforcement generation and detailing, you are able to document, you do your schedules of your reinforcement so that you can send to the fabricators, or you can have an idea of your quantities, the material takers and everything. And then the documentation is provided. This can be provided in cloud, or you can send this to the fabricator to do your steel, or the contractor to see what's going on. So this is really, really good. Everything is in cycle with an integrated model, so you can see everything. And we will talk briefly about BIM business process map in BIM structural engineering. This is a business process map. The business process map in BIM industry is typically, it tells you where, what, how to proceed with your use of the BIM, you know. So the process map for this is a process map for structural design company without a BIM. When there is no BIM, see how chaotic it can be. You get the information from the architect give it to the senior engineer, and the senior engineer translate it to the junior engineer, and he translate the junior guy translated to the designer. The designer send it back to the senior engineer for some modifications, and after everything, after all the design, then they send it down to the foundation engineer, because the foundation engineer will need the reaction forces from the entire structure to design his foundation. So he has to wait for these guys to finish. So you can see this process, how it's a little bit difficult, but with BIM, you have a central data repository. Everybody can see what's going on here. We can work from the repository. The foundation guy can be waiting, this guy completes, but he at the same time is able to determine what's going on, and he can predict, oh, this is how my foundation system will be analyzed, you know? And everybody is here in the middle, and you have this BIM repository working with it. This was developed by MF Mueller or in a project data interoperability assessment, but we made some modification to this. So the benefits of BIM in structural engineering, we talking about productivity. Obviously, this is obvious. When you have, you are able to synchronize your system, you have an integrated system working where you don't have to repeat. You automatically, that relates to production. You are being productive. Coordination and consistency of data. Your data will be streamlined. It will be consistent. You already know what is in, what is out. Visualization and simulation from the structural engineering point of view. As you see here, you are able to see clearly. I can visualize my reinforcement. I can really see the spacing of the reinforcement. This is really important. And I can simulate my structures to see the behavior, to understand the behavior. Documentations, the projects can be documented in just one system. Repository, we are able to document, and we are able to exploit the analytical model that will be the transition from the BIM to the structural engineering software. BIM is also creating the platform for third-party developers and downstream innovations. Got like something like Dynamo. Dynamo now is when you have a complex geometry, you can use Dynamo, you can use Grasshopper, you can use these tools to prepare the geometry of these, and then send it to Revit, and then do your analysis with it. And there are many downstream technologies that are coming up, like CI engineer is for structural engineer. It has something we call auto converter. You can convert your structural model automatically, and then you are able to identify the mistakes and things. So many things going on there. Yeah. Challenges. Obviously, there are some challenges. You have time and resources challenges. Complication with structural engineering. So structural engineering is a challenging field. The structural engineer must have a good understanding before he implements BIM. Otherwise, you cannot just have somebody building the geometries and models and say it's a structural model. If it is not corrected from the beginning, it's going to be really difficult in dealing with that. And there is no need for BIM if the guy, if the model has got many errors. It needs constant modifications. Yes, you require the knowledge to avoid all of these. Too much knowledge is required. Analysis link, yes, most of the links work to be able to connect the BIM to the FEM software, the structural software, but some still do have some problems. These are challenges. It's still not yet seamless. So we will be presenting 2 case studies. These 2 case studies are based on direct link interoperability. As I mentioned earlier, we have 3 interoperability in BIM structural engineering. Generally, the 3 most important that people use: the native file exchange, the direct link interoperability, and the IFC. But this project try to understand the efficacy, the effectiveness, the fidelity of the direct link interoperability. How is it when I use my Revit software, when I put my model in Revit software and I send it to a structural engineering software, how does it work? Does it receive all of the data correctly? This is what these 2 case studies about. And the first case study, it tried to test the direct link exchange between Revit and FEM software by testing and reporting on the data exchange scenarios between Revit to Surface Stick Revit to RFEM, Revit to CI engineer. That's why you have these case studies from A to C, as you will see along. The second case studies uses the Revit Sophistic interface to examine the efficacy of the structural engineering BIM workflow by designing the first flow slab as a subsystem from the main system. So we have like three levels, three flows of the models. So we just extract the first flow, and then we design the slab following, we design the slab following the entire structural design cycle, from scripting in Dynamo to modeling, analysis, design, detailing, and documentation. So we want to use this second case study to understand how Revit and Sophistic are really able to design the structures following the traditional structural engineering design cycle. So does BIM really work? When you place BIM in the design cycle, does it work? So we want to see that. This study want to try to uncover that. And this is a case study. It's an office and industrial complex designed for the cigar manufacturer Philip Morris in Bologna, Italy. The case study was provided by this company, as I mentioned earlier, Politecnica Ingegneria e Architettura. They provided me the data, all of the materials to perform an analysis. And this is a building was constructed in 2013 or 14, few years ago. It is currently in use. This is the building. So the description of the case study model, this is the building as it is. And this is the model the company created in SAP. They use another software, SAP 2000. And I use another software. And this is the case study models I developed in Revit. And then later on, I change it with other FEM software, as you will see later. Case study one, from A to C. A has to do with Revit to Sophistic. B, Revit to RFEM. C, Revit to CI engineer. So what I'm going to do is that the Revit model is here, and we exchange it with Sophistic. We observe, we see the changes. Whether Revit model is able to directly exchange this data with Sophistic, and how Sophistic receive this data. What happened? Was there any change? If I take the model from Revit to Sophistic, am I able to use that model? Is it sufficient if I take the model back to Revit? Is it okay to make additional changes and bring it back? What is happening there? We will see in these case studies. This is the basis of this study, as you're going to see along. That's why you have direct link. We use the direct link. It's not native file or IFC. These are the structural parameters for the case studies. The company provided me these data, and then I have to streamline this data for a case study. This is now total design in its entirety. I have to modify it, make some modifications so that it can represent a case study and it can be done as fast as possible. So we have the dead load, the live load, the wind load, and there was seismic load or earthquake, because the building was built in Italy, but then we canceled that because there won't be time for that. If we're going to go deep into that, it's more like going to be like a structural engineering. We didn't want this to be more about structural engineering. It's more about data exchange, but obviously our structural parameters must be correct. Yeah. So we adapted the concrete material properties. The design was done based on Eurocode 2. Eurocode 2 has to do with the steel concrete structure design. And I use C30, C37. The C represent concrete. These are the material parameters for concrete C30. And reinforcing steel, I use the B450 in accordance with EC2. These are the material parameters for that. Too much of that. Load and boundary conditions populated in Revit. In Revit, as I told you earlier, this is the analytical model, which is the transition. It is this model we're going to send to the FEM software. So now, as you can see, the analytical model is ready with all of the loads applied to it. You can see the dead load. These are the one in the maroon color, like red. And the live loads, they are the yellow ones. The wind loads are the green ones. The snow load is there, but you wouldn't see it because it's small. It's gray color. And these are the boundary conditions. As I told you, boundary conditions are necessary in order to perform a structural calculations. Everything is ready to move. But before that, we have to do load combinations. And the load combinations we do is at ultimate limit state according to EC2, which is the Eurocode 2. I did 24 load combinations. What is load combination? Load combinations in structural design is when you want to design a structural element. This is uncertainty. So you assume that with this structure, so many series of load will act at the same time, or some load will act, some load will not be present. So you combine all these scenarios like a probability. What's the probability that when everybody is in the hall, what happened? How the building react? What's the possibility that half of the people in the hall, what happened to the structural element? So the Eurocodes provide provisions to combine all of your loads. So when I did a combination, I came up with 24 load combination. When you have when the dead load is there, the live load is acting, and then you take a fraction of the accompanying load, the snow or the wind, when the live load is acting. So this is the general formula. The G stand for, the G is for dead load. The P should be, I think, pre-stress, but we don't need that. And then the Q is for live load. And this part of the live load has to do with maybe when you have a live load and then you have a wind load acting or a snow load acting, you have to take fraction of it, so the combination act together. So normally when you do this combination, you combine multiple cases so that you can get the worst case scenario, because for design we are looking for the worst case. What's going to cause a structure to collapse? We try to look for that in our design. Then when you do that, you are trying to be on the safe side. Then this will give you the worst internal forces, and based on these worst internal forces, you are able to design your structures. You put resistance against your structure, that is the reinforcement that would make the structure to stand, and the size, the thickness, and everything. So for the limit state design, this is a concept in Eurocode. There are two types: the ultimate limit state and serviceability limit state. Ultimate limit state design takes care of, if you just want to look at, you want to design a structure based on the safety, or the safety of the structure and the people, so that the structure cannot collapse when there's a strong wind. The building in Johannesburg cannot collapse because there's a strong wind, or when there's an earthquake in an Italian or China, the buildings cannot collapse. This, you look at ultimate limit state, mainly the stability of the structure. If you look at ultimate limit state, but you want to look at where there's this tall building in New York, and when there's a wind, this building should not deflect too much. This, you are looking at serviceability, the functioning of the structure, the comfort of the people. The building should not shake, or the bridge should not shake too much. The appearance of the construction works. All of these are taken care of in serviceability limit state. So when you are doing the structural design, these are the two conditions you will take care of. There's not much time to really go deep into this, but this is just the basic. Case study one, what we try to do, directly interoperability, the direct link data exchange between Revit and Sophistic. Now is Revit and Sophistic. We take with Dynamo, we move to Autodesk, we create the model in Dynamo, we move to Autodesk Revit to populate the data, to put more materials in the data, and then we create the central BIM models in Revit, in Autodesk Revit. Then we take the model from Autodesk Revit. We use the physical models, and then it's been converted to analytical models, and we send to Sophistic for design. What are we interested in? These are the data in this process. Does the structural model exchange properly? The material properties, the boundary conditions, the load cases, and load combination. These are the things that are necessary for this, for FEM calculation. If we are not able to transfer these from Revit to Sophistic, then that means your calculations will not go ahead. So we are interested in understanding how the software interprets these important structural data. These are the relevant structural data to a structural engineer. And this is why IFC has some problems when you want to perform an structural analysis using IFC, because sometimes some of these data are not transferred properly. So this is a Dynamo script. As you can see here, I created it here, and I automatically I was able to generate this, the model here. And this is Revit Sophistic directly interface panel in Autodesk. So this is Sophistic panel. How do you get this? You can ask for 30 days. You can sign up onto Sophistic website. You ask for 30 days trial version. Or you can also, as a student, you can use your admission letter. You request for 1 year. You are able to download this for free. But make sure you have Revit installed on your desktop. When Revit is installed, and then you have this installed, it's going to ask you, do you want, when you open Revit, it's going to ask you, do you want to connect Sophistic to your Revit? You say yes, and then you continue. Automatically, you will have this interface. So now, as you can see, Sophistic is embedded in Revit. So you are able to you are able to work here. You are able to perform your BIM model analysis and your structural analysis one platform. That's why you have one interface, multiple analysis. This is the workflow. The BIM models in Revit, you send the BIM models, the analytical models to the FEM in Sophistic, get the FEM, perform the analysis and design. You send the result here back in the same platform in Revit. You explore the result, you question your internal forces. How is it? How are the stresses? Whether is the right one? Is this my model correct? You send it back again to Revit, and you can make documentations and whatever you need to do. So as you can see how cool it is. Before, this was not really possible. In one interface, you can do multiple analysis. You don't have to create parallel file. You don't need to have two files here and there. Everything is synchronized in one system. This is really good. So when we do this, this is the result we get, result to Sophistic, Revit to Sophistic result. So as you can see, for the geometry, all of the geometries were transferred correctly. This correction mark, I'll show you the legend. This means everything was excellently transferred from Revit to Sophistic. This means before the transfer is done from Revit to Sophistic, maybe some minor modification has to be done in FEM. Maybe you need to change some material parameters. So for that, you take half of the point, asterisk and a correction mark. This means that no transfer is possible. So we come to the geometry, we were able to transfer everything, Revit to Sophistic. Material properties, Revit to Sophistic, everything was correct. The boundary conditions, correct. The low cases, all of the low cases were transferred directly as it is in Revit to Sophistic. The combination of the load, as we did it in Revit, it is in Sophistic. And then we are able to calculate the result back to Revit. We are able to bring the result back to Revit and analyze it. It was done correctly. So that was for Revit Sophistic. Now Revit for RFEM. RFEM is a Duluba software. The name of the company is Duluba, but then they produce RFEM for final element analysis. So Revit to RFEM, the same data of interest, all the same data we use in Revit to Sophistic. How does RFEM receive them as well? The same with RFEM, you can get the student version or you can get a trial version, and this is the you create the platform is created, right? The panel, the interface panel is created in Revit. Everything is here. You can see export and you can see import. You can export it to RFEM, perform your analysis, and bring it back to Revit and do further analysis of results and keep your BIM model result in it. This is really good, but then you have to do some settings here to make some modifications. The workflow, Revit to RFEM workflow. So as you can see here again, the same. We have the model here. We send it to RFEM. This is how it looks in RFEM, very beautiful colors. And we do the analysis and design, and we send it the result here again. And then we come back here in the cycle. When you bring it here, there's a problem. You are able to take it back and change it and bring it again. Come here, take it back and change it. One interface, multiple analysis, result. Again, the geometry was correct, the transfer, the beams, the column, the slab, everything. The material properties were done, but there's a problem with the material strength. Here, in the case of RFEM, you need to make little modifications. You have to set, before you do the transfer, you have to make some changes so that the RFEM materials is able to receive the Revit material. There's some little modifications. It's minor, it's not really complicated. But the material strength was not for reinforcing steel was not clearly defined. It was not exact as in Revit. So it doesn't have, it was wrong there. And everything was correct. So this is the result. Again, Revit and CI Engineer, another one. We do the same process, the same data, the same. You can also go on CI Engineer website. You can get a student version, or you can get a 30-day free trial, and you install it on Revit. And this is a platform. It's going to ask you which code you want to use, which exchange you want to do. The same process. Revit, FEM model in CI Engineer. The result exploration, back to Revit. One interface, multiple analysis. The result, the same. But the material strength is the same. You have to make some changes. First, in CI Engineer, before the analysis is correct, but I was not able to, the material type for reinforcing steel and the strength was not able to receive directly as it is in Revit. They have their own naming system. So that was not correct. So that's why you had it, but the rest was okay. I mean, all of the software, okay. So comparison of result. As you can see, when it is correct, it's one mark. If it's half, you get 0.5. Not at all is 0. So I do this comparison, Revit to Sophistic for the geometry, 100% from both sides, from all of the three analyses. For the material properties, Sophistic got 100%, Revit RFEM get 50, Revit CI Engineer got 37.5. For boundary conditions, all are correct. The load cases, all are correct. The load combination, all are correct. The calculation result back, when you take the result back from the FEM to Revit, all went well. So finally, Revit was 100%. So that means Revit with Revit to CI to Sophistic, you are able to perform an entire, with one platform, you are just able to do your BIM analysis, and you do your structural engineering design in one platform. Very cool, with no problem, 100% fidelity. And then RFEM 90% is also okay. It's also very good. Just that you need to do minor modification, which doesn't take more than 10 minutes. And CI Engineer 88%. There are still some modifications going, but all are okay. All is okay. All is very okay. Now with this result, this is why Revit Sophistic is interested in my research, and this is why these companies do this kind of research, because they want to understand how their software are working, how they want to get a feedback to make improvement. So this result is being shared with Sophistic, and also all of the TV software companies. They're going to see it. They know now what are some of the problems, what they need to improve on. Yeah. The second case study, the last case study, is basically, as we said, since Sophistic, Revit to Sophistic was the most, carry the highest score. So I use that to perform an entire structural engineering cycle design. So that's what the second case study is about. So it's not just to test whether the data were transferred. Here, we are interested in as well the entire design cycle. We want to see how the design is done also. So we get the BIM model, we get the analytical model. As you can see this time around, this is a slab of the first floor. We extract, and then we analyze it in the FEM, and then we do the reinforcement detailing, and then we do the documentation. The analysis and design of the first floor slab as a subsystem using Revit Sophistic. Yeah, the same. The data are populated in the central BIM model. When you click here, you're going to see all of these. The column is, you're going to see the properties, the materials of the column. This is really cool. This is what we call BIM, the data. You have all of the data. Facility management will use this in the future, years to come. You just need to click on it to know the materials involved. If he wants to change something, this is really good. Analytical model, this is the slab of the first floor with load. The loads are acting on it, and this is why we're going to transfer to the FEM. FEM system, now you see this is the analysis. What you see here, this beautiful coloration is the live load. So we do the alternative live load design, where we put the live load, we assume that the live load is here in the middle of this room, and these rooms are empty, and then we assume also that the live load is here, this one is empty, here, here, until we see the effect of different scenarios. There was another scenario, the live load is on all of the floors. There is another scenario, the live load is here, is alternating so that you can see the worst effect, yeah, to do your design. Now, we now have reinforcement area. We computed the reinforcement area from static calculation. So computation of the reinforcement area, this is the bottom reinforcement and this is the top reinforcement. So as a structural engineer, you can see this and know the problem, where the problem is, and you can query this. You are not just a BIM guy, but you know what the numbers are. You know the numbers. So based on these numbers, and for simplification purpose, we we look at the maximum reinforcement area, which was 6.3, and then we just design the entire structure, the top reinforcement and the bottom reinforcement. We use it. So with this, you see everything. So because we have the maximum reinforcement for all, we decided that okay, the top and bottom reinforcement. This is a case study. We don't need special. We don't need to go into detail. So we just use one reinforcement area. Normally, the reinforcement area is in centimeter square per meter. The maximum is 6.3, and we use that 6.3 to come here. This is a Revit sophisticated reinforcement setting. So with this setting, you see top exterior major direction of the reinforcement. Now, provided reinforcement, we provided 6.7. Our reinforcement area was 6.3. So we say, okay, 6.7 is okay, it's on the safe side. So you see now the provided reinforcement is greater than the required reinforcement, 5.6. We chose diameter 16 by diameter with a spacing of 300 millimeters. And for every side, the top reinforcement, the bottom reinforcement, this is what we provided, and you are able to see everything. This is really, really cool. Some years back, this could not have been possible. So with this, we are able to generate the 3D reinforcement. Now you can see now the 3D reinforcement. From 3D reinforcement, again, we can obtain the 2D detailed drawing. We use this detailed drawing now to do the drawing, the construction work. So this is the elevation of the slab. You can see how the reinforcement are arranged. This the detail of the reinforcement here. Some years ago, this was also not possible. As a structural engineer, you can look at this and say, okay, you can definitely see where the problem is, where there's no problem. This is really good, building information modeling. This is the aspect we were talking about, simulations. You are able to do your analysis and it helps. Everything is synchronized. With this information, you are able to generate your documentation, your schedules and your documentation. Your schedules are the rebar, the quantity takeoff, the material takeoff, what's the quantity of it. You are able to know now you are able to estimate how much money you're going to spend for reinforcement because you already know the total weight in kilogram with this. So what we did, we get the estimation from Revit and another one from Sophistic, and we compare both were the same. Very good. As you can see, the Revit total weight schedule gave us 8,136.86 kilogram. Sophistic, 8,137.9 kilogram. When you compare, both are very similar. Yeah. So this is what you're going to use now. These are the kilogram of the steel used. When you get to the fabricator gave you this, and this is where they're going to do the pricing, how much is going to cost per kilogram. If you are able to document this, send it to the fabricators, the fabricator, and then you send it on the construction fee. You can also have this in cloud. You already know everything. You document everything. This is what BIM is all about. So we now go to the conclusion. But before the conclusion, I would like to just demonstrate a little bit of this workflow, the second case studies briefly before, so that you can see real life what is it all about. Now, as we've already mentioned, here you have it. Beautiful. This model was built with, we use Dynamo scripting to get this model. And because there's not much time to apply all of these and run them, so I wouldn't want to waste time on that. And then we did some modifications in the Revit platform. So as you can see, the beauty of BIM, if I click here, I can see the metadata, all of the important data of the column, they are all here. For example, if a facility management, after the construction of this project, if we send this project to the guy who is the facility manager, when he wants to do a repair, he wants to do a reconstruction, refurbishment. He just need to come and check this data to know which grade of concrete we use. And as you can see here, the grade of concrete is here. And he wants to know what is the dimension, the cross section of the column of the first floor. You don't have to go anywhere. You just come to the BIM model, as you can see here. So additional information can be found here. Beautiful stuff. This is the essence of BIM, and that's why we say this is the central model. The central model, Revit allows you to build the central model. The central model is in Revit. All of the data is in Revit, and then you can move these data from one software to another. But then you always come back to the original central model data. So this is the central model data here. Now we now move because we are now going to the second stage, which is what? The analytical model. As you see here, this is the analytical model. And as I told you, when you are designing or you are modeling your 3D for structural engineering purposes, you must activate the template. For example, when you go to here, if you want to create a new project, you need to activate this to structural template. Only when you activate structural template, you are able to automatically generate this analytical model. And it is this analytical model, as I mentioned earlier, that is going to be transported or exchanged to the Finite Element software program for analysis. So as I also said, this analytical model, it serves as like a transition between the BIM model, the central BIM model, and the FEM software. So the analytical model is present with all of the loads. You can see this is how we apply the wind load to it. We just took wind load from one direction. The magnitude of the wind load is here. And these are the dead loads in the maroon color. The yellow color, the live load. These are the live load. As you can see, we have different scenarios of the live load. We have live load 1 acting all together, live load 2 acting alternatively, and live load 3 the same, as you will see this later. And we have the snow load here. It's very small. You're not able to see it. This is it. Yeah, the snow load. So now the model is ready. It's ready to go for analysis. But because we say we're not going to analyze the entire structure, it is not our interest to analyze this entire structure. We can only run this structure, and then later on we select the first flow slab to analyze. So I have already done that. I have already analyzed the entire structure, because before I analyze the first flow slab, I need to perform analysis of the global structure. Then I go to analyze the first flow structure. So with much ado, I move to the first flow. We extracted. This is the first flow. We extracted this. Revit Sophistic allows you to do this. Yeah, this is how to do that. How to extract this. It will tells you. You can okay, subsystem. You come here, and then it will tells you to either by law or by selection. But because I'm not interested in that for now, I cancel that. But this is where to go. You can select what you want to analyze. So we go back to our flow of interest. Now, can we see some things here to verify? Now we are in the finite element panel of Sophistic. This is it. It is embedded in. These are the ribbons. These are the icon we need to follow. So we go to material. We want to see how Sophistic receive Revit material. As you can see here, the documentation carries my name, and you see Revit material, concrete C30 to 37. C means concrete. This is the material I selected in Revit, and Sophistic receive it and interpret it exactly. A map, it did a mapping. So the same material. The default reinforcement material in Revit, Sophistic it does the mapping, and it was correct. Simple. There's nothing much you need to do. Okay. We go to sections, the cross section. See? Revit, Sophistic. Trave is an Italian word. It means the beam, 500 by 600 in Revit. This is a naming convention. I created my own naming convention, but the cross section is 500 by 600. For sophistic cross section, B over H, 500 to 600, the same. Pilastro, column, it receive it, the same. The mapping is perfect as you receive it, and it's been mapped correctly. You don't have to do any changes. Just make sure you do the right selection and do the right data input in Revit. Everything will be easily and seamlessly transferred. Okay. Now we go to, we do one thing. Now we move to this analysis settings because we want to perform the analysis. So let me say BIM Harambee. Let me say BIM Harambee Punto Africa. So this is the name of the analysis, BIM Harambee Africa. So then I will have to come here. It's already frozen because I've already selected the Euro code, which is the EN. If you want to select the code from South Africa, you want to select the code from China, Zimbabwe, the American code, the ACR, the BS, the British Standard, everything. If your code is in the software, it will be here. So in this case, I selected the Euro codes. So selection of the Euro codes, and then because we are interested in concrete, that's why the selection of AN buildings has been selected. This is a 3D FEA model. FEA stands for Finite Element Analysis, which is the senior Finite Element Modeling. So we go, here we are. And then we do what? Analytical check. Yeah. We want to see whether the analytical component of this has an error. If it doesn't have an error, we move on. No error detected. Good stuff. Then we now go to our analysis. As I told you before, analysis, we have analysis and design. You analyze to get the internal forces and stresses, then the design to size the members. So general. So the system is asking us, create boundary conditions and support elements, yes. Includes loads transfer from the acting system, yes. Spatial 3D system, yes. And it's apply the loads, yes. Analyze load cases, yes. And here, it is asking us enable self-weight for low case, for the low cases. In this project, we are not going to allow the finite element model, sophistic, to determine the self-weight. In my Revit model, I have already determined the self-weight. I have already input the self-weight, so I'm not going to include this at all. Go to geometry, export the various, you wanted to export the grades, the levels, yes. Meshing. If you recall earlier, I mentioned about the finite element, and the finite element analysis, you need to do meshing. The size of the mesh, so that the system can perform the stiffness analysis and displacement, all of these things at the nodes. So you can take 100 millimeters, 200 millimeters, 300 millimeters, or 500 millimeters. It depends on the kind of analysis you want to perform. It also depends on the kind of results you want to get. Sometimes the lower the mesh, the results, it gives you, it gets a little bit slower to get a result. The finer meshes, sometimes you get a good result, but sometimes the system runs very slowly. So I decided to take 500. Good. And the answer, perform linear analysis of load cases, yes. Analyze load combinations, yes. Take all of the combinations from Revit and bring it to Sophistic. What we do, calculate. Yeah. Okay, beautiful stuff. Calculation is complete. Now we've already calculated we have already done the analysis. So the next step now is we go to the design, which is here. Sophistic SSD means Sophistic Structural Design Desktop also, or Sophistic Structural Desktop. We click on this and the desktop opens. Yeah. This is a desktop open, and we now have this desktop. This is the what I need to do now is this is the how you say the analysis. This is the analyze part. I'm not yet ready to do the design. I would just like for you to see how the stresses are. For example, let's go to the low combination, the low cases. As you can see, directly we imported in Revit. It is here appearing in Sophistic. The dead load, you see the dead load action, the live load, you see the live load 1, live load 2, live load 3, you see, live load 3 is alternating. And we consider low combination 1. Yeah, you combine all of the load, the combination 1. But I think from my analysis, if I'm not mistaken, the worst combination was, I think, combination 12, if I'm not mistaken. No. The worst combination was combination 3, combination 1 and 3. So that's where we base the design on. Now we go to the design. This is the design part of Revit. Yeah, code check and design. So this guy here, code check and design reinforcement of concrete. So it's going to ask us, as you will recall, I told you we have two limit state condition in design. You have the ULS, which is the ultimate limit state, and you have SLS, serviceability limit state. But in this case of this project, our focus is on what? ULS. So we go, and then we are going to design the combination based on the ultimate limit state. We don't have to follow all of these because it's just a case study. You can do manual import. You can select the one you want. I say, okay, select all. So calculate. Okay. So the calculation is performing. The design, the system is being designed. So the design is complete. You will see here, the program has ended because the design is complete. So when the design is, we are done with the design, you might want to see the result or you want to question the result. What are the results? We come to report. So design ULS area elements. And yeah, see this. So here we are. These are the results. So let's go to upper reinforcement. As I told you, as you initially, this is it. You see, the maximum reinforcement area is 6 centimeters square per meter. This is the reinforcement area. It's always measured in centimeters square per meter. This is it. If we go to the lower reinforcement, almost around the same. And you can question the result, all kinds of internal forces you can question from here. So I don't want to waste much time here. And this, so from this point, we this is the same interface, but now we are in sophisticated component. But as long as we save the result, it's going to go back to sophisticated. So now we move back to sophisticated now to do the what? We've already done the analysis design, and now we're going to do reinforcement detailing. So we go back. Here we are now. So what next we need to do? We now need to do a reinforcement. The system has already been designed. It's already done the calculation of what needs to be done, the internal forces and the kind of reinforcement required. We now need to input based on our results. So we go to reinforcement generation, reinforcement, sophisticated reinforcement. So create, yes. Now we come here and you see BIM Harambee Africa, the data we've already done, beautiful stuff. Design case, it was one low case, ultimately listed, and then it tells us select model, selection of the model component. We select. You come here to select. You finish. Yeah, beautiful. And then as you see, the slab. Now, you see now what we were talking about. The selection I show you in the presentation. This is it. Tap reinforcement exterior. So because I told you this is a case study. We just took the maximum reinforcement area and designed the entire slab, the bottom, and we put the bottom reinforcement and the top reinforcement. They were all based on the maximum situation because we didn't want to do detailing. So just look at one situation. So we go. So the top reinforcement, our selection was 16 diameter, 16, yeah, 16 millimeter. With a 16 millimeter diameter, the spacing was 300 millimeters. As you can see, We go here, 6 in diameter. Top reinforcement, the same. We import. Yeah, yeah, yeah. Bottom reinforcement, the same. Yeah, yeah, yeah. Until you complete everything. As you can see, this is really good. Some years ago, 5 years ago, when we used to study back then, do structural analysis, the calculation would never take you to this level. You just do internal forces design, and then you do manual calculation of the reinforcement spacing and everything. But now everything can be done just from one point, from one interface. You can do everything. But now, this is where the judgment of a structural engineer comes in. Having determined all of your internal forces and you already know your reinforcement area, you are able to say, okay, since my reinforcement area is, I obtain, for example, I obtain a diameter, the area of my reinforcement is 6. I selected 6 point something. You have provided reinforcement 6.7 and the required reinforcement. So the reinforcement are provided is more than the reinforcement the system is requiring. So as a structural engineer, you are able to question all of these things. So this is not just about BIM. That's why we mentioned in our conclusion, for BIM structural engineer to take place, the designer needs to have a really good knowledge in structural engineering so that the work can really flow good. So from there, we can say, okay, but no need to say, okay, we already ran this, and you can come to your reinforcement. As you can see here, the reinforcement are all done here. Yeah, they are done here with the spacing required. Everything is done. Later on now, you can question this again according to the code. Euro code has specification when you do the reinforcement, how to do the lapping, how to lap the reinforcement, how to anchor the reinforcement from one structural element to another, from the beam to the column, how to do this anchorage. Everything is defined in the code. You have to go according to that. What the software does, or what it just done for us here, is that it only make your work easier. It just automatically compute all of the reinforcement required based on your area of reinforcement. So it is you now as a structural engineer or a BIM modeler to put this into context, into real structural context, following your code, whether it's American codes, whether it's the Euro codes. And then when you are done, you compute, you do the documentations, and then you do the 2D reinforcement, as we mentioned. There's not much time to go into all of that, but this is really important. One interface, multiple analysis. What all used to be difficult before, everything is now simple, and pretty much we are done with it. And that's it. And then the next stage, we move to the conclusion. Here we are. The study is done, and the intent of the studies, we identified 3 key levels of interoperability or data exchange method available to BIM structural engineers. With these methods, we also validate the direct link interoperability as the most effective and efficient method for exchanging data between BIM two authoring tools and an FEM software. As you can see in the analysis I have done all over, I mean, it's really powerful. And the correctness of data exchange between Revit and the 3 FEM software shows that Sophistic 100%, RFEM 90%, CI Engineer 88%, which is very good outcome. And we were able to test the effectiveness of Revit Sophistic interface in providing the full structural engineering BIM workflow. From modeling to analysis, design, detailing, documentation was tested and validated in the second case study, as you saw. The BIM using structural engineering for interdisciplinary coordination, documentation, and analysis and design. BIM in structural engineering, the benefits, to recap, you have productivity, coordination and consistency of data, visualization and simulation, documentation, analytical model, downstream innovation, etc. Some challenges, of course, time and resources, too much knowledge, analysis being a problem. Structural engineering BIM workflows also enables users to customize their workflow that is convenient and able to follow through, easy to assess, query, and audit your model. It's always good to have a BIM workflow for a structural engineer, and we mentioned a couple of it in this platform. It is also very important. It's very important at the concluding point to your BIM modeler or the guy who is in charge of the structural BIM model. You should have an appreciable knowledge in structural engineering to enable him to understand if this model is working or not. Otherwise, the beginning of the creation of the model, when there's an error, is going to affect the whole process. And that means BIM is no longer important, because the essence of BIM is productivity. So if you have a wrong model in the end, it's all over. So this is the conclusion. This is where we are. I want to say thank you to the Erasmus, the European Master Course, for giving me the opportunity, and the three collaborating universities, Mino, Ljubljana, Politecnico, and for Sophistic for the partnership in this thesis, and also Polytechnical Engineering. And a big hats off to BIM Harambee Africa for this initiative. Keep it on. This is very worthy cause, and we are always available to join you at any time. And we really, really appreciate this initiative. Thank you all, for all of you who listen to this platform. And I really do appreciate it. Thank you very much. Thank you. Bye.